Fluvial Systems and Channel Fields Part 3. The objective of this slide is to show the estimation of channel width to thickness ratio for a given channel system. Now imagine on the upper left section what we have here. Imagine that we have a channel system that does this, right? So the width is moving from one end of a bank to the opposite bank right across it. So the distance between this from this point A to point B is called the width. Now the thickness will be, so supposing we have this as the water level or the top of the channel field, the vertical distance from this point to the deepest part where you hit the rock below, or the sediment surface below. So the whole of this is actually called the vertical thickness. Now the width to thickness ratio is actually very key, because kind of what is used to classify the channel as weakly confined, confined, or distributary or distributive. Now this is a width to thickness ratio is taken from a number of modern analogs and modern channel fields and channel belts. So what we see is that in this chart, coastal plain inside valleys has a width to thickness ratio of approximately 700. Modern channel belts are lesser, from 70 to 300 range, give or take. And at the scale of the channel field, we actually have a much lower ratio, in the values of 10 to 20. Now these are really very these are much larger scale application, but at much smaller scale, the width to thickness ratio is very important in classifying the channels into confined or weakly confined or distributive channel systems. So what we're saying is that if a channel it's got this, for example, geometry, this is the width and this is the thickness. So in this case, it's confined, right? In some other case, you might actually have a system that is very extensive, like sheets, deposits. So I mean, those are more like if you for example, if you start looking at a distributive lobe like this, an individual lobe that goes and becomes very distributive more in the distal part, from the up deep to the down deep, or for more like basinal areas. So the width to channel ratio, width to thickness ratio here will be different. As you go further out, it's going to be a lot larger here, and then as you go even further out here, it's going to look more like a sheet deposits. So in that case, the width to thickness ratio will be very much higher than what you had for the confined case. So this will be high, or whatever that number is, but this will be much higher at the scale of the channel field. So this is a video. I'm just going to play you a video that shows a typical meandering analog taken from some surface gullies that were seen in an outcrop visit done recently. So if we keep going, this goes back to what we had discussed in our earlier episode. So this will be, if I take a profile that does this, and then this would be the other part of the system. So right here, so this would be a typical inner bank, right? So the whole of this deposit will be called the point bar. And then right opposite it will be the outer bank. Actually, or cut bank. Right. So the thing is, whatever we had coming through the whole of this fairway is going to make this angle hit this part of the wall and then bounce back. So while we're getting things deposited on this side, on the opposite of it, everything here is getting eroded. So overall, we're going to have very steep angle on this side and very, not so steep angle on the inner bank. I'm going to just take this back. So starting from the beginning, this is what we get. And let's keep going again. Same thing, right? So in this case, this will be the inner bank, and that on the other side, everything here is the outer bank. So we have deposition on this side and erosion on the other side. Right, so thank you. That's what we have for this episode. Please do not hesitate to send your comments or questions, and follow us on YouTube and Facebook.